All right, ladies and gentlemen, welcome to Chapter 18. This is the last lecture out of Ralston Valley High School Chemistry's AP lecture series here online. Let's get started. This is going to be a discussion of radioactive decay and nuclear equations. So happily for you, nuclear chemistry is a topic which we hit fairly heavily in first semester of your first year of chemistry, and therefore most of what we're going to be looking at here today is just a very brief review of some material that sometimes does show up on the AP test. So we'll focus on kind of the key ideas, and those in particular involve writing nuclear equations and the concept of a half-life, which we've discussed earlier as well. So let's get started here. In nuclear chemistry, we are dealing with changes to the actual nucleus of an atom. There are two main modes of changing the nucleus. Those are via either fission or fusion. Nuclear fission involves the splitting of a larger, heavier nuclide into two smaller particles. Generally, they split into nuclides with similar mass numbers of one another. The reverse of that process is starting with two smaller nuclides and forming one heavier, and that process we call nuclear fusion. That is the familiar process, which essentially is the energy source of our sun, in which hydrogen is fused into the heavier element of helium. Now, the reason why a nuclear fission might occur within the nucleus has to do with the relative forces of attraction and repulsion that occur within the nucleus itself. So thinking about the nucleus, recall the particles present in the nucleus are protons and neutrons, so we're not worrying about electrons in the electron cloud at this point right now. And within that nucleus, we have the familiar repulsive force that exists between the protons, that is the force of electrostatic repulsion between like charges. And if that were the only force that were acting within the nucleus, then every single nucleus would be inherently unstable due to that repulsive force, and those nuclei would essentially blast themselves into pieces. And obviously not every nucleus does that instantaneously, which implies, therefore, there must be something holding that nucleus together as well. And there's another fundamental force of nature that's probably somewhat less familiar to you that actually is at play there. The force of attraction which holds the nucleus together is referred to as the strong nuclear force. It is a fundamental force, just like gravity or electrostatics. And that force is a force which generally acts over very, very, very small distances on the order of magnitude of the size of the nucleus itself. And that force becomes rapidly weaker the greater the separation of the particles. So you can think of it kind of almost as a balancing act. On the one hand, we have the attractive force of the strong nuclear force holding the nucleus together. On the other hand, we have the repulsive force between the protons, which again would cause that nucleus to split apart. And so it's really a function of both the relative strength of those forces as well as the actual geometry of the nucleus and how close together those protons and neutrons really are that tells us about the stability of the nucleus. And if that nucleus at some point is unstable, we see a greater repulsive force existing between the particles within the nucleus, it's likely to undergo a decay, and in doing so, spit out a little particle, finding the nucleus in a lower potential energy state. Now, there's a variety of different types of radioactive decay that can occur. Last year, you were probably familiar with the ideas of like alpha decay and beta decay, which we discussed in great detail. But this year we're going to explore a couple other modes of decay here, including positron emission and proton and neutron emission as well. And if you have a look at this graph that we have here to the right, we've graphed here a essentially table of nuclides showing the type of decay modes which are dominant for different nuclear species. You'll notice that depending upon where you are above a kind of line of stability through the center there, different modes of decay tend to be dominant. For example, if you have a nuclide that has a relatively higher number of protons compared to its atomic mass overall, so a kind of a high proton to neutron ratio, in general, that type of species will undergo either a positron emission, which is a beta particle we'll talk about momentarily here, or an alpha emission if you get to those particularly heavier nuclides towards the bottom of your periodic table. Conversely, if we find ourselves to the left of that line of stability that runs through the center, in those instances we have a relatively smaller number of protons compared to the number of neutrons in the nucleus, and we see the dominant mode of emission as a beta negative emission, which you might recall last year as the emission of an electron. So I've never actually seen an AP test question reference this chart of nuclides, but it's just a kind of nice, neat thing to know, and also just keep kind of in the back of your mind about why certain types of decay might be likely to occur for a particular nuclide. So we'll move on. All right, here we have a table of different types of radioactive decay that can occur from a nucleus. Recall from last year, we defined radioactive decay as the spontaneous emission of particles and energy from unstable nuclei, resulting in the formation of those particles and at the same time giving off energy, lowering the overall potential energy of the nucleus itself. We've got a variety of different decay products we're going to be examining here today, and we'll move through these fairly quickly because these are things you have seen from last year, just as a brief reminder of things which you are familiar with from earlier. Starting off with the most familiar types of emission, the first one we have here is what we refer to as an alpha decay or an alpha particle. A symbol we use to notate those in our nuclear equations is the Greek letter alpha, and the mass of that alpha particle is approximately 4 atomic mass units. Which makes sense because those alpha particles, as it turns out, are essentially the nucleus of a helium atom. That is, it has 2 protons and 2 neutrons for a total mass of 4. And as such, we will notate that within our nuclear equations, if you recall, with the mass number up top in the left-hand corner, mass number of 4, and then the lower number represents the atomic number of this particle, which in this case is an atomic number of 2, notating those 2 protons. And we're going to go ahead and give it that symbol He within our equations here, notating again that it is a helium nucleus. And do note and remember that that alpha particle itself is a charged particle because it is only the nucleus of the helium atom. That is, it doesn't come with the corresponding 2 electrons like a normal neutral helium atom. Conversely, we have a different type of particle here for the second type of emission here. This is a beta emission, symbolized by that Greek letter beta. The mass of a beta particle is essentially close to 0, not exactly 0, but very, very close to 0. And that makes sense because, again, the beta emission is the emission of a high-energy electron from that nucleus. And that might seem like a kind of weird idea because, again, we're talking about the nucleus emitting an electron here, and the electrons are not normally found in the nucleus. They're found in that cloud around the outside. But we can understand how a beta emission occurs by thinking about the actual process of beta emission on our next slide. Beta particle emission is the result of an emission of a negatively charged particle from a neutron. And when that neutron emits an electron, the electron that it spits out carries with it the negative charge, meaning the neutron itself becomes more positive and thereby turns into a proton. So beta emission really results from neutrons spitting out an electron, turning themselves into protons. So the nuclear equation symbol we use for that beta particle, again, we're going to give it a mass of essentially 0. It's not truly 0 because the electron is matter and does have mass, but it's close to 0 on the atomic mass unit scale. And we'll give it an atomic number of -1, notating again that it has a negative charge rather than a positive charge of a proton. And we'll give it that symbol E, notating that it is an electron. Now, a second type of beta emission, sometimes we call this beta positive emission here, is what we refer to as a positron emission. A positron is essentially the antimatter equivalent of an electron. That is, it has the same mass and is like in all other aspects except for its charge. The electron is a negatively charged particle, and that positron is a positively charged particle. And positron emission is a little bit less familiar to us. We're more familiar with the normal types of matter we see around us in our daily lives. But it does occur and actually does have some uses that we can make use of as humans for imaging in particular, for like medical imaging. And that positron emission, we're going to give it a symbol beta as well, but we're going to give it a little beta positive there, notating that this positron has a positive charge. So essentially 0 for mass again, and now a +1 charge. We're still going to give the little E symbol. And beyond knowing that these exist, you'll learn more about positrons and other exotic types of particles if you go on to study modern physics in a college course. But for the time being, just notate that that is one of the modes of decay that we can see occur from atoms. Another process that we didn't really introduce to you last year, but is one I'd like you to be briefly familiar with here, is what we refer to as electron capture. You can kind of imagine electron capture as being the opposite of a beta negative emission. If you think about squishing matter into a very, very, very small space, you can imagine the point where the electron itself might be absorbed into the nucleus itself. And if you take one of those electrons into the nucleus and squish it into a proton, what you would end up with is essentially a neutron, since the positive and negative charge would balance one another out, and you would end up with a neutral particle overall. This is the sort of event that occurs in very, very high pressure scenarios in places like, say, the formation of a neutron star after the collapse of a star in a supernova. So electron capture, essentially the reverse process of a beta negative decay. A couple more emissions here. A gamma emission goes by the symbol Greek letter gamma there. Gamma emission is essentially the release of a photon of light, and it accompanies a lot of these other processes. So oftentimes when you see something like an alpha emission or a beta emission, you might see something emitting gamma particles at the same time. The gamma emission, again, emitting a photon of light, is really just the emission of energy from the nucleus of the atom. And what that really tells us is if we're not really spitting matter out of the nucleus, but just energy, that event must really accompany a kind of a rearrangement of the nucleus of the atom. Again, because if it spits out energy and energy is conserved, that means the nucleus must now be a lower potential energy. So you can think about it kind of as like a reshuffling of the relative position of the protons and neutrons within the nucleus, resulting in a drop in energy of the nucleus, which means that energy is going to be carried away from the nucleus as a photon of light. And then two last familiar ones here. We've got proton emission and neutron emission. They're exactly what they sound like, spitting out either a positively charged nuclear particle or a neutral nuclear particle. We can fill in their symbols here for a proton, either 11H, notating one positive charge with a mass of 1 AMU, or 11P. Those are both used. For a neutron emission, mass of 1 but charge of 0, and a symbol N within our nuclear equations. And those emissions, again, are more familiar particles than some of these kind of more exotic ones we've discussed earlier. So those are the types of radioactive decay you're likely to see on the AP test. Now let's practice a couple of problems on the next slide here, showing how we can write these decay equations. All right, here we have a brief look at a couple of review problems from last year on spontaneous nuclear decay. Real familiar problems here. First one, we're going to show a balanced nuclear equation describing the emission of an alpha particle from an atom of francium-212. And if you go ahead and notate on your page here, the atomic number for francium from your periodic table is 87. We'll go ahead and put that in the bottom left-hand corner. And then the 212, the mass number for this isotope, in the upper left-hand corner there, along with that symbol Fr. Now, in a nuclear decay, the parent nuclide is going to end up emitting a particle here, in this case, which is an alpha particle. That alpha particle, again, is the nucleus of the helium atom. So we'll notate it within our equation with a mass of 4 and a charge of 2. And then there's going to be some daughter nuclide that remains behind after this decay event occurs. And the key idea in solving these problems is that we're trying to show conservation of matter. That means that the amount of stuff we start with in this process really has to equal the amount of stuff we end up with. Now again, note that it's really not matter which is conserved in this system, it's really energy that is conserved. But we're going to be kind of ignoring for the time being the small changes in the mass of the nuclides due to their relative potential energies for the time being. So it looks more or less like we were seeing conservation of matter, even though that's not entirely the case here. So starting off here, when we look at conserving our mass in the system, if the parent particle had a mass of 212, we ejected a particle with a mass of 4 AMU, that would imply that the daughter nuclide must have, therefore, a mass of 208. Or another way of looking at it is the sum of all the particles created on the right side must equal the initial particle's mass that we began with on the left. Same thing must be true for charge. Charge is also a conserved quantity. And again, looking at francium, we have a total positive nuclear charge of plus 87 with those 87 protons. The ejected helium nucleus of that alpha particle had a charge of +2, and that implies that the daughter that remains behind must therefore have a nuclear charge of +85, which we could then look up on your periodic table and find that is the element astatine that is formed as this process of nuclear decay occurred. And again, note that this is really kind of the long-term goal of what the alchemists were trying to achieve here. That is, we have changed the nucleus of one atom into another. We've transmuted an element to form an entirely new elemental species. All right, so that's alpha decay. Second example here, let's look at example 2, this time a beta decay. We're going to go ahead and write the balanced nuclear equation describing the emission of a beta negative particle, that is electron ejection here, from an atom of antimony 129. So same process as before. Start by writing your parent nuclide, and we'll get that on there. Antimony is the symbol Sb on your periodic table, atomic number 51. And we've got our mass number there of 129, so we can notate that. And again, we are ejecting a particle here, so let's go ahead and show our ejection. And on the product side, the beta particle has a mass of essentially 0 AMU and a charge of -1. And that implies, therefore, that the daughter nuclide is going to have the same atomic mass number, same mass number as the parent there. That is, we're still at a mass of 129, since the ejected particle had essentially no mass. But to show conservation of charge here, note that the charge of that beta particle was -1, and therefore to show conservation of charge, I would have to take that sum of -1 plus 52 yields the same overall total positive charge of +51 that we began with on the left side of our equation. And that implies, therefore, the new daughter nuclide here has an atomic number of 52, which makes this now an atom of tellurium. And again, we can note here that both the parent and the daughter have the same mass number, but the daughter has one additional proton. That is, the atomic number has gone up by 1. And the only way that that could have occurred, again, is if the neutron in that nucleus turned into a proton, again, by emitting that electron. So there is a beta negative decay, and those are by far the most likely two modes of decay you're likely to be tested on within the AP test itself. All right, now a different type of problem you might come up against on the AP test is what we refer to as a collision problem. Whereas those two previous problems were the result of spontaneous emission of particles from the nucleus, those are spontaneous decay problems, the alpha and beta decays. These problems are problems where two nuclei collide with one another, resulting in kind of like an atomic scale train wreck. So we can use this type of problem to understand events that occur within a place like a particle accelerator, where we essentially accelerate small nuclei to very, very high speeds and then smash them together in order to synthesize new elements. So this type of problem is going to show the exact same process as the last one. That is, we're trying to show conservation of both charge and mass within these systems. And really the key to solving these problems is to just figure out what's missing within your equation. So take a look at our example 3 that we have here. We've got two examples of these collision problems here for you. In the first of these examples, looks to me like we are currently colliding some mystery particle here with a helium nucleus. And that collision results in the formation of a new isotope here, which is berkelium-243, as well as a neutron. So the first thing I'm going to do in this process is I'm going to go through and fill in whatever information I can find for the atomic numbers of these species off of my periodic table. So to begin with, we've got that helium nucleus right there, so let's go ahead and throw an atomic number of 2. That is the atomic number for helium down below. And then find on your periodic table the element berkelium, which is found on the very bottom table there of the table in the actinide series. Its atomic number is 97, so we'll throw that in there as well. And then the neutron, again, recall, has mass but no charge, and therefore we'll give it its atomic number of 0 within this process. So we filled in the information that we currently have. Now let's go about showing conservation. Looking, first of all, at mass within this system. On the product side, the total sum of the mass numbers of the particles present is the 243 plus 1, yielding a total mass of 244 in the system. And again, because mass is essentially conserved in these, even though some amount of the matter will be transformed into energy, we can go ahead and assume that the total mass of the system before that collision occurred also must be the same 244 that it was after. Given that 4 of that mass of the system was taken up by the helium nucleus, that implies that the remaining 240 must have been the mass number of the other particle involved in the collision. And we can apply that exact same logic as well to charge. The total charge on the right side of our equation, on the product side there, is our 97 from the berkelium plus 0 from the neutron. So we've got a total charge of 97 on the right. There was a charge of 2 from the helium on the left, which implies the other particle must therefore have been accounting for 95 of those positive charges in our system. So we've got an atomic number there of 95 for our mystery particle. And if we look up on your periodic table, you can find atomic number 95 as americium. So we've got americium with an atomic number of 95 and a mass number there of, again, 240, must have been the particle involved in that collision. Same logic we can apply for the second example here. And this time we're looking for the smaller particle that's colliding with here our isotope of californium-249, resulting in the formation of dubnium-260 and 4 neutrons in this system. So, just like before, let's fill in all of the information we can, and then we'll go ahead and solve for the missing particle. So looking up on my periodic table, I find again in the actinide series, the element californium right after its neighbor there, berkelium. You can probably make some guesses here about which lab was responsible for the discovery of some of these particles here. And we find californium is atomic number 98 on your periodic table, so we can fill in that piece of information. Looking a little further along there, we find now the element dubnium. Dubnium, who is here listed on our table as the particle with an atomic number of 105, I believe. Yep, there it is right there. So we've got 105 for the atomic number of the dubnium. And then again, those neutrons, 4 of them formed here, but each of them has an atomic number of 0. So with the information now filled in, we can go ahead and do some math here to figure out the particle that must have collided. Looking again at the right-hand side, the mass of dubnium, 260, plus the 4 neutrons gives us a total mass in that system of 264. And looking on the left-hand side there, we've got californium with a mass of 249. So to get from 249 up to 264, that looks to me like we would need a total mass of 15 for the colliding particle in this system. And now we can deal with, again, our atomic number. On the right-hand side, the dubnium, again, has an atomic number of 105. The neutrons have no positive charge there, so we can ignore those. So we've got 105 total positives on the right-hand side. So to get from californium at 98 up to the dubnium at 105, that would be a particle with an atomic number of 7. That is 7 positive charges present right there. So this looks to me now like an isotope of nitrogen, nitrogen with that atomic number 7 and a mass number in this case of 15. So we've got nitrogen 15 as our colliding particle that shows both conservation of charge and of mass within this system. So there you go. All right, so having now taken a look at both collision problems and at spontaneous decay problems, the other big concept you might come up against within the AP test itself is the concept of half-life as it relates to nuclear decay. You spent some time during our kinetics unit talking about half-life in chemical reactions, and here we are going way back to first semester of your first year of chemistry here to talk now about half-life of nuclear decay problems. And the key idea to note here about the half-life of these nuclear isotopes is that the time it takes for half of a sample of a radioactive substance to decay is going to be a constant value for a particular isotope. That is to say, it doesn't change depending upon how much of the isotope is present. And that's a property, as it turns out, of a kinetic system that is exhibiting what we refer to as first-order kinetics. If you recall from back in chapter 12, we learned that first order kinetics displayed constant half-lives for a particular reaction. And because all of the nuclear decay have constant half-lives for each particular isotope, that implies we're really here kind of starting with something we already know, which is we're going to be dealing with first-order kinetics, which is kind of nice that we don't have to worry about whether we've got some sort of weird zero or second-order process which is occurring here. Note here on your periodic table of the elements that we gave you at the start of last year, up in the top of that periodic table, there's a list of selected radioactive isotopes that list for you both the half-life as well as the type of emission that tend to occur with particular nuclides. Now, that being said, also note that your actual AP test periodic table does not have one of these useful little inserts there. So if you are going to be talking about an AP test question involving nuclear decay, they're going to have to provide you with information about half-life of these particular isotopes. Now, doing some math involving these problems is going to be relatively friendly here, noting that we already are familiar with the idea of how first-order kinetics work. Recall that for first-order kinetics, the rate of decay is equal to a constant, and please, again, be very careful to note here that K is the rate constant, not the equilibrium constant. So the rate of decay is equal to the rate constant times the number of nucleotides. And that's something that should kind of make logical sense. That is, if you have a large sample of radioactive material, you would expect to see a large number of atoms decay within a given amount of time, just given that you've got a lot of them decaying. If you have a smaller sample of matter, the number of decaying particles within a given amount of time would also, again, obviously be smaller. So it makes kind of sense that we'd expect then to see first-order kinetics for this process. And down below here, in addition to that standard rate law, I've also given you here a integrated rate law. Again, recalling that for first-order kinetics, the integrated rate law showed a straight line relationship between the natural log of the number of particles and time as that reaction occurred. So we end up with that equation again. The natural log of n, where n represents the number of nucleotides, is equal to minus kT plus the natural log of the initial number of nucleotides. And again, note that that is in y equals mx plus b form, where on the y-axis you have the natural log of the number of nucleotides, and on the x-axis you have time, and the slope of that graph is equal to minus k, where k again is the rate constant for your nuclear decay. And long story short about these, the shorter the half-life for a nuclear decay, the less stable the nucleus actually is. So half-life can essentially be used as a shorthand to talk about the stability of an atomic nucleus. All right, and as our last little look here, we're going to take a look at some half-life practice problems here. We'll show you two methods of solving this first one here, and these methods should be familiar from your first year chemistry class last year. The first of these methods is what we're going to refer to as the chart method for solving a nuclear decay problem. So in this problem, we're going to ask you here to calculate the final mass of a 10 milligram sample of iodine-125 after 360 days have gone by, given the half-life of iodine-125 is 60 days. So, the key to solving most of your half-life problems is to solve for the number of half-lives that have gone by. And once you've got that information, there is either an equation which we can use, or you can just use kind of the logical chart method to solve for your answer, depending upon the particular setup of your problem. So let's take a look at both of these methods here. First things first, if the half-life is 60 days and 360 days have gone by, that tells me, therefore, that the number of half-lives that must have eclipsed, therefore, have been a total of 6. That is 360 days divided by 60. Gets me 6 half-lives have gone by. I'm now going to go ahead and set up a little T-chart here. And on this T-chart, on the left-hand side, I'm going to have the number of half-lives that have gone by. And on the right-hand side, I'm going to have the mass of my sample remaining at that point in time. And important to note here, folks, I'm going to put as my first entry into this T-chart, the number of half-lives that have gone by is going to start with 0, that is, at time equals 0, no time has currently elapsed. And on the right-hand side there, I can have the amount remaining of my sample, which in this case is going to be 10.0 milligrams. And all I'm going to do at this point now is go through and, after each half-life, cut the amount that I have remaining in half. So again, after one half-life, I should be down to 5 milligrams remaining. After 2 half-lives, I would be down to 2.5 milligrams remaining. 3 half-lives would bring me down to 1.25. And 4 half-lives should bring me down to 0.625 grams of iodine 125 remaining. 2 more to go. 5 half-lives brings me down to half of that remaining amount, which would be 0.3125 grams remaining. And last but not least, final one here, brings me down to my final amount after 6 half-lives of 0.15625 grams remaining. And excuse me there, I misspoke. Those units should be in milligrams rather than in grams. And I got to be really careful here with sig figs here, noting that the significant figures present in my half-life time there of 60 days is literally one significant figure, which really means I need to round that to the nearest one sig fig in my answer there as well, which puts me at the not super accurately measured here 0.2 grams remaining. So far so good. Pretty easy process just of thinking through logic to get to your answer in the end. Now, to derive an equation for this process, note here that how I found my final answer here was essentially by multiplying my initial amount that I started with by a factor of 1/2 n number of times, where n in this case was the number of half-lives that have gone by. And so from that, we can essentially just translate that into an equation. The final amount, we'll call this NF for number of particles remaining at the end, then final, would be equal to the number we started with, we'll call that n sub I, times 1/2 to the n power, where again, n is the number of half-lives that have gone by. And the nice thing about that equation is in this equation, you are not constricted to dealing with whole numbers of half-lives. So the chart method will only work when you have a whole number of half-lives that have gone by, whereas the equation method will get you to the correct answer regardless of whether that's a whole number or a fractional number of half-lives that have gone past. And again, we could see in our equation here that the equation would come out to the final amount, n sub f, would be equal to the initial amount of 10 grams times 1/2 to the 6th power, which again, plugging into my calculator, I get the same final amount there of 0.15625 grams, again, rounded to 0.2 grams with our sig figs. And excuse me again, those are milligrams, not grams. So there you go. That's a half-life problem for a kind of quick and easy way of solving those. All right, and very last slide here for our lecture. What I want to look at for a last idea that you might kind of come up against on the AP test is the use of graphical data to derive some numbers that you might be asked about on relating to half-life here. Have a look at the graphs which I've made for you right here. The first graph shows a graph of the percentage of the remaining undecayed atoms that remains versus time. And each of those data points that's plotted here, you'll note, is taking us to half of the amount that remained from the previous data point. That is, we went from 100% to 50%, then from 50% down to 25, from 25 down to 12.5. And what you're seeing right there is essentially a data point plotted at each half-life. So looking at your graph, one piece of information which you could extract from a graph that looks like this is that the half-life of this particular element, as graphed here, looks to be about 60 days or so, noting again that the amount of time it takes to go between each one of those half-lives off of your x-axis there looks right around 60 days. So you can derive the half-life of a particular isotope by looking at a graphical analysis of a percent versus time graph. Likewise, we can also get some useful information out of the graph on the right-hand side there, in which we've graphed the natural log of the percentage of undecayed atoms remaining versus time. And you'll note here that this graph of the natural log of the percentage remaining versus time yields a straight line graph, which again is a characteristic of first-order kinetics. And recalling from your first-order kinetics that the slope of that graph has a slope of minus the rate constant k, that means that I can essentially derive the rate constant by looking at the best fit line for that straight line graph, which you'll see there. I've used to find there with a value of k, which would give me a k value of 0.0116 in that instance. And again, recall from your unit on kinetics that the units on the rate constant k for a first order reaction are the inverse of the time units used on your graph. So in this case, that would be inverse days. Oftentimes, again, it'll be inverse seconds because that's most commonly what you'll get on these graphs. But for this particular graph, it is inverse days. And therefore, our rate constant k would be 0.0116 inverse days for this particular reaction. And you also might recall from looking back to chapter 12 there that we derived from you in a previous slide of a previous set of notes the equation that relates the half-life and the rate constant k for first order kinetics. That equation was that the half-life time is equal to the natural log of 2 divided by k, or how they will actually write it for you on your AP equation sheet. That half-life, again, is equal to 0.693, which is an approximation for natural log of 2 divided by the rate constant k. So again, if you got the graph that you got on the right there on your AP test, from that graph, again, you could find the rate constant k by using the idea that the rate constant k is equal to the negative of the slope there. And once you found that rate constant k, you could then plug in that rate constant k into your half-life equation and then use that in order to actually solve for the actual half-life time of your particular isotope right there. So a couple different ways we can manipulate graphical data here in order to extract some useful information that the AP test might be looking for. And that brings us to the conclusion of your final lecture here in Chapter 18 on nuclear decay. Thank you very much for listening, and good luck on your AP test.